talk in this tutorial a little bit about how things like plate tectonics change the surface of a terrestrial world like Earth. A lot of these processes are going to be in common with objects further out in the solar system, like the icy moons of the Jovian planets, where it's not molten rock, but cryovolcanism. So water and other hydrogen compounds changing phase from liquid to solid, providing these sort of resurfacing processes in tectonics. All right, Earth's changing surface. The extremely high temperature of Earth's core causes material in the surrounding mantle to become hot, expand, and rise toward the surface. So that's convection. The mantle material then cools and sinks, resulting in a circular motion of material moving beneath Earth's surface. So there's one convective eddy and another convective eddy. The circulation of mantle material causes the continental and oceanic plates to move across Earth's surface. At various locations on Earth's surface, we are able to observe plates colliding, plates separating, and plates moving horizontally with respect to each other. The drawing below shows a cross-section of Earth's surface and its underlying mantle. At this particular location of the surface, the dense oceanic plate is being forced beneath the less dense continental crust. So this is subduction. The dense oceanic plate experiences higher temperatures and pressures. It is forced deeper into the mantle. This interaction between the oceanic plate and the continental plate causes molten material to move upward through the continental plate until it breaks through the surface in the form of volcanoes. All right, so I'm going to answer a few questions based on this figure. In the drawing above, positions A through D show the position of 4 pieces of mantle material. Use the drawing to answer the next 3 questions. Which direction, right or left, are the oceanic and continental plates moving? So the oceanic plate is being carried to the right. And our continental plate, we've got a convective eddy that at the top is going to the left. Which is hotter, the piece of mantle at position A or the piece of mantle material at position D? Well, at A, it's getting ready to, in the future, it's going to sink. So that is colder and denser than its surrounding. And the material that's flowing past D is still coming up. So that has got to be hotter and less dense. So D is hotter. It is deeper and rising. What direction are the pieces of mantle material moving? Up, down, left, or right? At positions A, B, C, D. So A is moving to the right. B, I've got velocity down to the right of it and velocity down to the left of it. So that is moving down. C is motion to the left. And the last one, D, is motion up. Consider the following discussion between 2 students debating why the oceanic and continental plates move. Student 1. The plates are moving because the mantle material is constantly moving beneath Earth's plates, and this causes the plates to move. Student 2, I disagree. The plates are just floating on the mantle material. The plates started moving a long time ago when Earth initially formed, and the plates' momentum keeps them moving toward each other. So student 1 hasn't said anything incorrect. Student 2 sort of missed out on the previous page. It is the motion of convection in the mantle that is driving the plates to move. For student 2's idea to hold, this would be like motion where there was no friction to damp it out. So like Newton's first law of motion sort of idea. And that is definitely not the regime for motion of the continental and oceanic plates. There's definitely an awful lot of friction between the plates, one another, and between a plate and the mantle. All right, 5. Just beneath point I on the drawing is a tropical island. What will eventually happen to the island as the oceanic plate moves? Why? So this tropical island, once the plate, the oceanic plate, has been subducted all up to there, it is just going to get sheared off and it gets stuck onto the continent. So you just added an island to the continent. All right. Just beneath point C on the drawing is an ancient impact crater on the ocean floor where a giant comet collided with Earth. So it's like Chicxulub. What will happen to the ancient impact crater as the oceanic plate moves? Why? So this impact crater, eventually that is also going to be subducted underneath the continental plate. And everything there is going to melt again inside of the mantle. So that impact crater will be erased. Imagine that an impact occurred on the continental plate millions and millions of years ago, leaving behind an impact crater near the right side of the base of the volcano. Why would there be little evidence of this impact crater found today? So, before this continental plate was lifted up by the oceanic plate subducting underneath it, and this mountain range was formed, they're saying there's a crater there. You're not going to see that crater because I have a volcano right next to it. It's been filled in, and it's been uplifted due to the collision with its neighboring plate. So, while all of the rock and material that made up that crater is still there, it has been uplifted and it's been filled in by volcanic flow. So you're not going to see, at least from the surface, is looking crater-like or ish. All right. So we have a picture of the moon. Consider the image below of the rocky and crater-covered moon. Its very old surface has remained virtually unchanged over the last few billion years. Do you think the moon has an active, hot, and molten interior or an inactive, cold, and solid interior? Why? Oh, these craters are still all over the place, even where there are mountain ranges. I have craters. There's no sign of the moon being split into plates or those plates moving with respect to one another. So no harbingers of plate motion. And you have many craters. And that's indicative of a geologically dead surface. If a new planet were discovered, which that happens all the time, what evidence would you look for to determine whether or not it has an active, hot, and molten interior? Why? It's an easy thing to look for. Is the surface heavily cratered? If there are craters, probably not geologically active. Those craters had to have formed after that planet ceased being geologically active.